Hello, my name is Roman Jerger, and this is Transport 2, Homework 2. Today we will be discussing the question, a 10 centimeter long uniform cross-section capillary initially contains pure liquid water and deuterium on its left and right halves, respectively. At time is 0.1 seconds, the maximum molar diffusion flux was 2.78 moles per meter squared seconds. Pure deuterated water, D2O, molecular weight and density are 20 grams per mole and 1,110 kilograms meters cubed, respectively. Question 1. What is the overall mass flux corresponding to the maximum molar diffusion flux? Question 2. Make an order of magnitude estimate for the maximum driving force for diffusion at 0.1 seconds, and carefully sketch the initial, intermediate, and final mass transport profiles below following the textbook nomenclature. Question 1. In this problem, as previously stated, we are looking for the overall mass flux, N, at the given maximum molar diffusive flux. Mass flux is a mass, like grams, over meters squared seconds, which is a flow, through a certain area meters squared. Molar diffusive flux is similar to mass flux, but molar flux is moles per second, which is flow through an area meters squared. The diffusion flux differs from that of flux in that the flow that one component is diffusing into another component. When the problem dictates that the maximum molar diffusion flux corresponding with the overall mass flux is 2.78 moles per meter squared second, this means that each component is diffusing into one another with that diffusive rate. The overall diffusion rate, or the overall diffusion flux, will be zero. Because the diffusion has reached completion, there will no longer be a fluctuating gradient, because the question dictates that this is a closed system. We can then say that there is no net flow in the system. With the given molar diffusion flux of 2.78 of water, and the overall diffusive flux is zero, then deuterium must be negative 2.78 moles per meter squared seconds. Now the negative sign in the diffusive flux for deuterium is negative because deuterium is moving from the right to the left and water is moving from the left to the right. We now need to convert the diffusion flux to normal flux. This is the relationship between flux and diffusion flux for component I. So the molar component of I is equal to the molar diffusion flux of I plus the concentration multiplied by the molar velocity. The term CIV is the bulk contribution. The bulk contribution comes into effect if there is a net flow in the system. However, since this question is a closed system, there is no net flow, so this term is negated. That means that the bulk contribution is zero and the molar diffusive flux is equal to the flux, dictating that the molar diffusive flux of water and deuterium is the molar flux. Now we will convert the molar flux to mass flux. The mass flux is equal to the molar flux multiplied by the molecular weight. We then plug in the molar diffusive flux of water and deuterium into this equation and multiply them by their respective molecular weights. This gives us the mass flux for water, which is 50.04 grams per meter squared seconds, and deuterium to be negative 55.6 grams per meter squared seconds. To get the total mass flux, you need to then add the mass flux of water and the mass flux of deuterium, as we do in this equation. Now you can see that the total mass flux in the system is negative 5.56 grams per meter second. Now on to question 2. We are looking for the order of magnitude for the maximum driving force. The driving force is the strength of the diffusion between two compounds. This is the definition for the driving force for a multi-component system. However, we are working with a binary system, so instead of using this whole summation, we can simplify it down to this equation. Now, because the driving force of water and deuterium are going to be equal and opposite to one another, we will call the driving force D. D is equal to the molar fraction of I multiplied by the molar diffusive flux of J minus the molar fraction of J multiplied by the molar diffusive flux of I divided by the total concentration times the Stefan-Maxwell diffusive coefficient. Now, because the molecular fractions have to equal 1, we can then substitute xj, the molecular fraction of J, for 1 minus the molecular fraction of I. Now, as we've seen before, the total molar diffusive flux is equal to the sum of the separate molar diffusive fluxes, which equals 0. Therefore, the molar diffusive flux of I is equal to the negative molar diffusive flux of J. We then plug these variables back into the equation and we simplify it down to this term. We pull the molar diffusive flux of J from the previous question 1, or we can use it from the given question 2.78 moles per meter squared seconds. And we plug in the Stefan-Maxwell diffusive coefficient. This is determined through experiments, and as we discussed in class, for liquids, the magnitude for the Stefan-Maxwell diffusive coefficient is 10 to the negative 9th meters per squared seconds. Now, the only term we need to find is the concentration, which we then use by determining the concentration, which is moles over volume. We convert the density of water and deuterium into moles, and we divide it by the volume. Now, since we are not given a volume, we assume we start off with 1 cubic meter of water and 1 cubic meter of deuterium. Now we plug this into the equation and we get 55,528 moles per meter squared for the total concentration of the system. Now we plug it back into this equation and you get the negative molar diffusive flux of J, which is negative 2.78 moles per meter squared second, divided by the concentration, 55,528 moles per meter squared, multiplied by the Stefan-Maxwell diffusive coefficient, 10 to the negative 9th meter squared per second, which gives you the magnitude of the driving force, which gives us the driving force 50,065 moles per meter squared. This then determines the order of magnitude to be approximately 50,000. On to question 3. Here we are determining the density, molar concentration, molar diffusive flux, and mass flux. These are now then broken down into 3 time sections, at 0.1 seconds and at 60 seconds, and then quote-unquote infinity seconds, which really means until the reaction has been able to fully mix. Now, to break down the x and y coordinates, on this y coordinate you can see that this represents density, both in terms of water and deuterium. Now on the x-axis, all the x-axes are the same, 0 to 10 centimeters. This is actually representing the entire capillary from left to right. And as you can see, on the left-hand side of the capillary, water is at its pure density because deuterium has not yet been able to make its way onto that side of the capillary. And that is also the same on the right-hand side, which is deuterium at 1,110 kilograms per liter. Now, once the reaction occurs, you can see at this intersection, this is right when the mixture takes place, where deuterium and water start to mix, and the density is approximately half. Now we move down, and we now can analyze the molar concentration. On this y-axis, we have the moles per liter, again, over the x-axis, which is the capillary itself. On the left-hand side, we have all water, and on the right-hand side, we have all deuterium. Again, this sort of mirrors the first graph. However, in the first graph, because the density of deuterium is higher and heavier than that of water, deuterium is ever so slightly higher on this graph than it is on this graph. Now, they start off at equimolar because we both start off with the same amount of water and deuterium. Now we move down to the molar diffusive flux. And as you can see, the molar diffusive flux on the left and right hand side of the capillary are both 0. This is because there is no mixture at these points in the capillary quite yet because deuterium and water haven't made it there. However, the molar diffusive flux, right when the reaction occurs, water is at its highest right here, right when the reaction takes place. And as you can also see, it is positive. That's because the molar diffusive flux is moving for water is moving from the left to the right, and deuterium, which is negative, is moving from the right to the left, indicating in which direction each of these components are moving. Now we will move down to the mass flux. Now the mass flux only takes into consideration the mass flux, not both deuterium and water. So the mass flux is negative right when the reaction occurs. And as you can see, again, both at the beginning and the end of the capillary, it is both 0 because there is no gradient and or mixture at those points. Now we will look at the reaction at 60 seconds. This is once deuterium and water has been able to mix, and there's a little bit of deuterium on the left-hand side, and there's a little bit of water on the right-hand side of the capillary. Now as you can see, deuterium is more readily able to move from the left to the right because it is heavier. It is moving more of its weight to the left to the right to displace water. And that is shown in this graph, this slight little bump right here. And as we move down, you can see the molar concentration. Now they're not quite as high on both sides because the molar concentration of deuterium on the left and right hand side of the capillaries has now been able to mix. Now there's a little bit of a gradient of deuterium and water throughout the capillary, but it has not yet been fully mixed. And as you can see right here in the molar diffusive flux is slowly starting to reach 0. This is because there's a gradient now between the entire capillary, and the highest peaks of the molar diffusive flux is right at the center, right where the reaction occurred. Now we'll move down to the mass flux, and as you can also see, it is going towards 0, the mass flux. And we know this because it is reaching towards 0 because once the reaction has taken place, there's no more mixture, there's no more gradient. Therefore, as time progresses, the mass flux will slowly approach 0. And as I just said, in this final right third column, once the mixture has been able to reach its full completion, we have mass flux equaling 0 and molar diffusive flux equaling 0. This is because, as I had previously stated, that there is no mixture occurring throughout the capillary, so the molar diffusive flux and mass flux must equal 0. Now, The molar concentration and density are obviously not zero at these points. However, the molar concentration is going to be linear because there's equal amounts of water and deuterium throughout the entire system. And this is also shown in the same graph where deuterium and water are right here. They're evenly spaced throughout the entire capillary. I'd like to thank you for watching this video. My name is Roman Jerger. I hope you have a great day.